tonight's webinar, being the last of the series, the last day of the series. And I hope it has been a very interesting journey so far. I believe we've learned a lot. I myself personally have learned a lot, and I believe you've learned a lot as well. Without wasting much of our time tonight, we are going straight to time series analysis with SPSS, and our own dear Oluchi piece is already waiting for us to take us through the journey of time series analysis. And I'm going to welcome her to the podium, yes, the virtual podium now. And I handle to Oluchi. Oluchi, please, you can start.
Good evening, everyone.
Good
Good
evening.
Good
evening.
evening, everyone. Okay.
Good
I
evening.
want
Good
to welcome
evening.
every one
Good
of
evening.
us to this last day of webinar, and I want to congratulate us for being consistent so far, and also want to thank God again for bringing us this far. And I just want to thank every one of us for staying glued to this space. Okay, so my name, as I said, is Oluchi Peace, and I'll be taking us on the journey of time series using SPSS. So, okay, let me share my screen so that we'll be able to start share. Okay. Can we all see the screen now?
Yeah, we can see the screen, ma.
Okay.
Yes, I can see.
Thank you. Thank you. Okay, so let's go to our slide for today. Time series analysis with SPSS. Okay, so now, without wasting much of our time, what is time series? Time series analysis is a statistical technique used to analyze data that is collected over time at regular intervals. It involves identifying patterns, trends, and seasonality in the data and making forecasts based on the historical data. Okay, let me stop here for now. So when we're talking about time series, we have two things: time, then the series. And let me take us back to our secondary school days where we have series and sequences. You remember when we have series, it's something that is continuous. It is continuous. Now let's bring it to time. When we have a data where the time is continuous, take for example weekly, monthly, yearly, it could even be quarterly. If let's say I want to if I want to check for a particular trend for a company, maybe a manufacturing company, I want to see, are they selling this week? Did they have or did they have high sale this week? Were they able to sell much in this particular month? Were they able to sell? Was their sales increasing or decreasing? That's where we use time series. Now it is used to identify the patterns, the trends, and the seasonality in the data, and as well as making forecasts. So when I have a manufacturing company data set now, let's say for maybe last year, and I was given the data set as an analyst, and I was asked to check if I should just study the pattern or I should identify the pattern in their sales. Now I can apply time series to actually check for this pattern. If I want to check for this pattern, and now I will introduce my time series. Now, for me to now see this pattern, I'll be saying, okay, is it that it is moving trend, it's moving by trend, that's linearly or even quadratic itself, but most times it's always linearly. I can also check, okay, was it seasonal? Do they sell in this month, and maybe in the next 4 months they won't sell, or maybe in the next 8 months they will sell again? You're able to study all these things due to because of a particular technique, a statistical technique called time series. So now from that data that I'm giving, I can even make a forecast for them, like predicts other values. So let's take for example, we have, maybe I was given just a 2 months data set for January and February. And now we are in March, and maybe possibly March, yes. Now I'll be asked to now, as an analyst, to forecast or to predict their sales, maybe how much they'll be making in June or July, whatever month it is. I can use my time series. So all these things together, when you put it into place, that is what the concept of time series is all about. When the data is ordered by time, I have my sales for this month, I have my sales for this week, I have my sales for this year, I even have my sales for a month, a quarter year too as well. So all these things put together is time series concepts. So time series data is commonly used in economics, finance, engineering, and other fields to analyze and forecast variables such as the stock prices, sales, production levels, and even the weather patterns. So all these things I mentioned now are where we can apply time series in, and there are lots more of it. So you can also make your own research on it. But majorly, these are the places, these are the important sector in country or in the world where time series is mostly used. So let's go to the next slide. So there are a number of things that are of interest in time series analysis. The most important one of them are the stationarity, the modeling, the composition, and the forecasting. We'll be coming back to this later on, but let's continue. So time series forecasting is the use of time series model to predict future values based on previously observed values. Just like the example that I gave earlier on, I am using an historical data that they've that's been taken time past. It is observed already. Now, based on that historical data, I am to predict, or I'm to obtain a model that will help me to predict or to forecast, or maybe sales or whatever thing for for that manufacturing company. So all these things, these four things are what we should always watch out for in our time series: the stationarity, the model itself, the decomposition of the time series data, and the forecasting as well. So now we have the components of time series. The main components of time series are, before I go into this one, before I go into the main deals, the main components, some textbooks, some sites, and other authors we say, instead of components, they'll be like types of time series. Everything put together, we are trying to classify how our time series data will always look like. That is what everyone is still saying. So your time series data can be trend, it can have a linear trend, it can be seasonal, it can even be cyclical, and it can be irregular. So when do we have a trend variation? So the trend component of the time series refers to the long-term pattern or direction of the data. A trend may be increasing, decreasing, or flat. For example, a company's sales may have an increasing trend over time. So now let's see this particular example now. So for this one here, it is a trend. Now you notice that at level one, at the first month, that's January, their sales was increasing, it was increasing, it was increasing. Then later on, at this point, at the eighth month, it dropped. It is a pattern, and it's also a trend. So we have the increasing part of it, and we have the decreasing part of it. So that is all about linear trend. So when we have seasonal variation, the seasonality component of a time series refers to the repetitive and predictable patterns that occur within a specific period, such as a year, month, week, or day. For example, the sales of winter clothing may show a seasonal pattern with higher sales during the winter months. Let's even leave this winter clothing. Let's go to the one we all know very well, Christmas period. During Christmas period, local transports, both airlines, that's airports, they will have increased sales. Why? Because during that period, it is an holiday period. So there is an expected increase in their sales, because virtually everyone, yes, will be going back to their homes. Everyone will be going to meet their families and all. So most especially for all these airplanes or and the local transport itself, you will notice that when you come to December period, they have a very high increase. So when it now comes after December, you notice that in January they might still be having the high increase, but come to February, where we don't have any holiday, their sales will decrease. I don't know if you are getting it. Their sales will decrease, because at that point in time, there is no holiday at that point. There's nothing like, okay, everyone go home or there is a break. No. Even if there will be a break, it will be like maybe 2 days, and you can stay in your own house, in your own individual house, instead of going to your family, your mom, dad, and everyone like that. So all this kind of time series is called seasonal, because it occurs only at a particular year, or at a particular month, or a particular week. But most of the time, like the example that I gave earlier on, that's of Christmas, it is monthly. So if you are comparing, let's say 2010 to 2012, you will notice that when you get to December 2010, the sales will increase. When you get to 2011 December, the sales will increase. When you get to that of 2012, the sales will increase. It is seasonal. Throughout all the years over time, we have an increase in the sales for during for Christmas, yes, during December. So that's what we call seasonal. So let's check the um diagram here. Now you notice at this point, the cold season is coming down. Now it's going up again. That's for the warm season. It's coming down again. You know, now this one is so obvious that it is a seasonal trend, because the way it comes down, when you have when you're in between the winter and the cold and the spring, you have the cold season. By the time you go up again, it's that will be within the fall, this fall year. So this is seasonal. So the same example, like the example we also gave here, the sales of winter clothing may show a seasonal pattern with higher sales during the winter months. The same thing. Now we have the cyclical variation. The cyclical components of a time series refers to the non-seasonal patterns that occur over a long period, typically more than 1 year. Now these patterns may be due to economic cycles or other long-term business cycles. So this cyclical, let's go to this diagram. Now you notice that from here in 1920, the annual production of bituminous coal, yes, bituminous coal is it was increasing at this point. Then it came down and it is going up. So for cyclical, all about cyclical is the way it fluctuates. It does not have any particular pattern. You can't predict that this is what will happen, this is what will happen. It just fluctuates. It can go high. It's just like this Bitcoin of a thing. Maybe today Bitcoin will go up. Before you know what's happening, tomorrow again, just because of Elon Musk did something, it will come down again. That kind of situation. That's when we have the cyclical part. Then we have the irregular. Now look at this diagram here. It is so irregular to the point that we can't even predict, or we can't see in between this line here. You will notice that there is a higher trend here, there is a higher variation here. Then when you come down, when you come back again, you see it's going down. It is just going up, going. It does not have a particular pattern that it is following. It does not have a particular trend that it's following. It just goes up, come down, goes up, and it just keeps on going up and down. And the reason why we have irregular variation is because of maybe unpredictable events. These fluctuations may be due to unpredictable events, errors in measurements, or other factors. So let me give us a very funny example. Not very funny, sha, but I'm a lover of Korean movies. So there's this particular movie that I watched that talked about forecasting weather. I don't know if any of us can relate to it. But in this movie, the movie is all about forecasting of weather. So it happened to be that there was a day they forecasted, like before they went home that day, the workers, that's the company workers, they forecasted and they gave it on the news that rain was going to fall the next day. Heavy rainfall. They were going to have heavy downpour of rainfall. But all of a sudden, that day, everybody has prepared. Everyone has gone out with their umbrellas. They've already gathered themselves up to use their umbrella. But all of a sudden, the next day came. Rain didn't fall. Why? We don't know. It is an unpredictable event. Like, you can't even say, okay, this was the reason why rain did not fall or anything. Now at that point, you can't fault anybody because we don't have a particular reason. Neither can you fault nature about it. So that one is irregular. So there are some times that when you have your time series data, you will just notice that maybe in January, maybe a local transport has an increase in their sales, and all of a sudden in February it's reduced. It's going in March again, maybe for week one it just went high. Maybe the second day of the week one it came down again. No regular pattern. It's just going up, coming down, going up, coming down. So, and when another thing again to note in irregular variation is when the fluctuations in the data cannot be explained. It is something that you can't help, and you can't even predict that. You can't even say, okay, this is the reason why I have this is why I don't have this. So that's about the components of time series. So these are the diagrams that we have. Then we have the time series models. So if you denote the trend with time, the trend with T sub T, the seasonal components with the seasonal with S, the cyclical with C, and the irregular or random components, which you can also refer to as the I. We can therefore express each observation as the additive model and the multiplicative model. The additive model for a given time series y1 to yn, that's for your data, is the assumption that these data are realizations of random variables yt that are them that are added. Sorry, there's a mistake there. That are added. Now when you add the four components, which is the trend, the seasonality, the cyclical, and the irregular, it gives us an addictive model. And when you multiply it, it gives us the multiplicative model. So moving onward, now we are going to the main deal: time series analysis. The time series analysis comprises of methods for analyzing time series data in order to extract meaningful statistics and other characteristics of data. The time series forecasting is the use of a model to predict future values based on previously observed values. We've explained that previously. Time series analysis focuses on comparing values of a single time series at different points in time. Then time series analysis can be applied to revalued continuous data, discrete numeric data, or discrete symbolic data. There are several approaches to analyzing time series data, of which we have the smoothing method, the decomposition method, model, the Bose-Jenkins time series model, and the autoregressive model for time series and forecasting. Where this one is very much applicable is when you are using a programming language such as R or Python. But for SPSS is not that robust to accommodate much things for time series. But for R, I'm very sure of R, you can be able to even perform this box Jenkins time series model on it, and you can use the aspects of this discrete numeric variable and the symbolic data as well for your time series analysis. Okay, so now a stationary time series. So a stationary time series is one whose statistical property, such as mean, variance, autocorrelation, etc., is constant over time. Most statistical forecasting methods are based on the assumption that time series can be rendered approximately stationary after some mathematical transformations have been applied. Now, before I talk about the transformation, what is stationarity itself? Before you can say I want to work on my time series or you want to analyze the time series data, you must watch out for something else: the stationarity. Remember from this slide here when we said there are some things of interest: the stationarity, the modeling, the composition, and the forecasting. So that's what we are trying to establish here now. So now, stationarity, a time series is said to be stationary if its statistical properties do not change over time. That's the mean and the variance, and as well as covariance. So by the time we start the practical, we will see how a stationary time series looks like and how a non-stationary series looks like. I have a diagram under here. Now look at this diagram. You will see that at point 0, all the old values that we have in, they are either coming up and going down, and they are not far away from 0 compared to the non-stationary. Now you see that this is 0, but they are farther away from 0 here. The same thing as well with this. For this one, you see that it was going, then later on we had it, then later on it's now went high. you know this one is not a typical, it's not a typical stationary time series compared to this. So when the statistical properties of a time series data does not change over time, that's when we say our time series is stationary. And before, one thing I want us to know is that before you can predict the values or forecast, you must have a stationary data. The normal thing is when you get your data, it might not look stationary, or it might not be seasonal, or no, sorry, your data will be seasonal, yes, and it will not be stationary. Now it is not left to you to now make it to be stationary and non-seasonal. Let me repeat it again. When you have your time series data, let's say I went on net and I want to download the time series data, and for a time series data, Okay, I didn't explain that. For a time series data, I must have my time as my independence variable, which can be measured in weeks, days, months, or years, or even quarterly. Now, I will now have the next variable, which will be the dependent variable, will be maybe the quantities. Take for example, I can say crude oil price. I can say the price of or maybe the sales of a manufacturing company, or even the gross GDP of maybe of Nigeria, of anything. But make sure that you are having a particular column that has your dates there. If you don't have dates and you carry it to SPSS and you say you want to run your analysis, just say it is gone, because it's just return error for you. Because you have to understand how your data set should look like before you say, okay, this is the analysis I want to carry, this is the analysis I want to carry. If it is in binary logistics like the one we did yesterday, we noticed that our dependent variable, our dependent variable was having the one and the zero. Now it is fit for a binary logistics analysis. The same as well for time series. You can't be using a logistics regression data set on, and you say you want to analyze for time series. Oh, you are wrong. You will get it all wrong there. So make sure that your data itself is a time series data first. And I remember, if let's say you download a data set and you want to take it to our programming expects you to tell it that, okay, oh, this thing, oh, this particular data set, convert it to a time series data for me using the ts command. If you don't do this, if you don't use the ts command, the time series results you'll be getting will be so wrong. It won't even be what you're expecting. I don't know whether you understand it. So you have to make sure that all these are very, very, very are complete. Now let's go back to the stationarity. So now when we now have the stationarity, okay, if your data set, now you've converted it to time series, good, that's fine. You've made sure that your date column is there, no problem. Now, if you now want to carry out the test and you now notice that you apply a line graph or a line chart, whichever one, and you now find out that my data is not stationary or it is seasonal. The next thing to do is to apply transformation. Now this transformation, we have two transformation we can apply, which is the logarithm transformation and the differencing transformation. Most of the time, with my experience, I have come to understand that most of the analysis that we do for projects, we stop at differencing of one. It is maybe for higher levels, that's when you see differencing to be equals to two. I don't want to rush us now, so let's just take it small, small. We'll be going small, small. So always make sure that your data should be stationary before you can carry out a time series or forecasting. Yes, and this is how a stationary time series will always look like. It will not be looking like this, but you will notice that it is the mean and variance of each variables and not further away from zero. Then, in other words, the constant mean and abi sorry, a flat looking series again without trend, constant variance over time, and a constant autocorrelation structure over time, and no periodic autocorrelation. That is how a stationary data set will always look like. So let's go back to, now we have the difference, just like we said before. The difference is a method of transforming a time series data set. It can be used to remove the series dependence on time, which is the seasonality. It can help to stabilize the mean, variance, and autocorrelation. That it can make it to become nearer to zero. So the series calculation of the series, yes, by removing changes in the level of the series. If you need to difference your original time series data d times, that's how many times are you differencing in order to obtain a stationary time series. This means that you can use an arima pdq model for your time series. So we have the AR, which is the autoregressive model. We have the moving average model. Then we now have arima, we have the AMA, that's autoregressive moving average. Then we now have the ARIMA. The ARIMA is the one that combines everything that I said before. So we have the P, D, then Q. So the D here signifies the number of times you've differenced your data. If you difference your data to be stationary as point one, that means your model will be having one as D at that point. That's that one. Now let's go to the next point. The most compelling aspects of autocorrelation analysis is how it can help us uncover hidden patterns in our data and help us select the correct forecasting methods. Specifically, we can use it to help identify seasonality, trend in our time series data. Additionally, analyzing the autocorrelation function and partial autocorrelation function in conjunction is necessary for selecting the appropriate ARIMA model for your time series prediction. So we have these two functions, the ACF and the PACF, which helps us to uncover some hidden ideas behind our data. Now, do you want to check more? If you want, maybe you want to obtain the value of your P and Q from the ARIMA model, you use the ACF function and the PACF plot to determine all this. And you can even use it for your time series prediction, because if you don't have that plot, there is no how you want to predict your model. No, I want us to remember that when I was saying, when we were talking about forecasting, we said we are forecasting based on a model we created from the observed value, that's the historical data. So the model we are talking about is from this ACF plot. This is where we get our forecasting values from. So the next thing is, now we won't be doing what I'll be explaining today is the ARIMA model. Based on my experience, this is the most common one that people always do. So, and for me, it is very straightforward to do compared to others. Though others are also okay, but this one helps to forecast more values than others too. So now the ARIMA modeling applies autoregressive moving average, AMA, that's the AMA, or autoregressive integrated moving average, which is the ARIMA models, to find the best fit of a time series model using past values of a time series. Now, the assumptions of ARIMA model. So before you start your ARIMA modeling, there are two concrete assumptions you have to lay. The first one is the discrete time series data must be equally spaced over time, and also there shouldn't be any missing values in the series. Just like I said, your time series data can be measured daily, weekly, monthly, yearly, and also quarterly. If you are now doing, let's say you want your first observation is 2020, January, okay, January 2020. Your next one is now maybe February 2020. It's still okay. The next one you have is maybe March, no, April, yes, April 2020. It is not spaced equally. And maybe the next one again is not like August, you're not putting September the next one. It is not spaced. Compare it to when you have, that's why time series has also given this opportunity to apply the quarterly data. So you start from January, February, March, April. The next observed one will be in April. So you take it 4 which is quarterly, or you take it monthly. But if you're not doing January, the next one is now February, the next one is like April, the next one is now June. It is not spaced over time. I don't know whether we are getting it. So all these things, all these assumptions must be established before you can carry out your time series and your ARIMA modeling. The next one is the series also needs to be stationary. We've explained that before. That is, the mean variance and autocovariance structure between the same number of time lags should be constant. That's, it should be closer to zero and it shouldn't be farther from zero. So let's go to the next one. Then the ARIMA model identification. Now, the following are the steps involved in the Bose-Jenkins model identification. Most times, we also refer to the Bose-Jenkins model identification as the ARIMA model too. So the first one is stationarity. Now, we are going to check if our data set is stationary enough. The next one will be differencing to achieve stationarity, or you can carry out your logarithm transformation, whichever one that you like. Then we identify the PDQ parameters for the ARIMA model. Then we'll build the model, and maybe lastly forecast as well. So I want to explain the autocorrelation for us before we go into the practical aspect of it. So now, the ACF is an autocorrelation function that gives us values of autocorrelation of any series that its lagged values. We plot these values and we have an ACF plot. Now the question here is, what is lag? So lag variable, they are just variables that are based on the past values of the time series. If, for example, my first observation for January 2020, and the observation I have, my value, or the observed value I'm having is 20, maybe 20 years, and the next one, which is February 2020, the next observed value is 24. For the third one, the next one is 25 or probably 30, whichever one. Now, when you want to establish the ACF plot, one thing is that that 20, the first value, will be shifted upward. Then now it is now going to be like a correlation between the other values, while the first one is being shifted up. If you are increasing the number of lags you want, no, all these things I'm saying, we are going to see it later on when we start the practical part. So when you shift, or when you are increasing the number of lag values that you want, for SPSS the default setting is 16 lag values. I can increase it to 20, I can increase it to 30, whichever one that I want. And as I'm increasing it, there's going to be a difference in my ACF plot. Why? Because a value is being shifted forward one or more time, or equivalently. Then the next values, now you're not going to find the correlation between the next two values, and like that till you get to the end of the number of lag values you've chosen. So that's it about the ACF. And the same as well for PACF. So when you get to your PACF, the PACF shows the PACF is just is finds correlation of the residual, which means after removing the effects which are already explained by the earlier lag. So the first one that you removed has been explained already. We've gotten that we've established a correlation between the first and the second one. Now the effect is what to be observed. Now when you now observe the effects of the first and second one, now the second and the third one will be observed again. That will be the registered one again for the PACF. So all these two functions are so important, because without, if you can't explain, if you can't if you don't understand the plot, you won't be able to get your ARIMA PDQ model, which is very important for our forecasting. So the next one is the moving average model. So in a nutshell, the moving average model, the autoregressive moving average model, and the autoregressive let me jump to this autoregressive integrated moving average. So in statistics and econometrics, and in particular in time series analysis, an integrated moving average model is a generalization of an autoregressive moving average model. So ARIMA uses the combination of autoregressive and the moving average. In between, we have the integrated. Now, the AR, the autoregressive, is our PACF. That means from our PACF plot, we'll be getting the value of our P. When you now get to D, we've explained D before to be the difference. Now, the Q, which is now the moving average, is now we can obtain that from ACF. We can obtain that from ACF, which is from the ACF plot. So, which is the value of Q. So as you are doing this you have to observe the values, the lagged values, and the lag variables, the number of lag. So all this PDQ, it helps us to predict and to also forecast using the model that we've created to forecast for new values. I don't know whether we understand it, but when we get to the practical, we understand better, please. So the information criteria. Now, how do we know it is possible? One thing about time series is you can have series of models. You can have series of models in the sense that, okay, I can assume, okay, let's say I applied one difference, and that's my difference is at point one. And I say, okay, my P is now 3 and my Q is 2. That's 3 ARIMA 312 model. I can have ARIMA 310 model. I can also have ARIMA 311 model. Now, how do I know the parsimonious model among these three? Parsimonious in the sense the best candidates model for forecasting for the ARIMA. How do I know the best one? That's when we have the information criteria. So we have the Akaike information criterion, which is the AIC, the Bayesian as well, which is BIC. But for SPSS, it is limited to BIC. Then for programming languages like R, we have the AIC and we also have the BIC. So let's go to the BIC, which SPSS will be giving us. So the Bayesian Information Criterion, or BIC for short, is a method for scoring and selecting a model. It is named for the field of study from which it was derived. That's Bayesian probability and inference. The statistics students can relate more to this. So the score is as defined above is minimized. That is, if let's say that is the model with the lowest BIC is selected. Now let's assume that my first model, which is ARIMA 310, and let's remember I have three models: ARIMA 310, ARIMA 311, ARIMA 312. That's PDQ, and I have these three models. The lowest BIC, the three models among them that have among these three models, the one that have the lowest BIC is the best candidate. That is when we can say, okay, this is this model we will use to predict our values. Now, when fitting the models, there is a tendency that some models will be competing. Thus, it is appropriate to use a model selection criterion to select the most adequate model. Now, to you might say, okay, the ARIMA 311 model is actually looking okay since I don't have whiteness, I don't have residuals that are beyond the the boundary line, yes, the significance bound. Now, but the application of BIC will make you understand that no, this option that you've chosen, the ARIMA 311 that you've chosen, is wrong. Why? Because it has the highest number of BIC. So that is why we say when among these three models, if the lowest one is maybe like 2.0, that means it is that model itself that is 2.0 that will be the best candidate to predict our values. So that's what BIC is all about. So in this study, we'll be using the BIC is employed. It's going to be employed to select the best adequate model. Now we'll be going to the practical very soon. So the procedure now is we open our SPSS software and click on the open data to import your data set from the file menu. So once the data set is loaded, so let's do it one after the other. So the first thing is to open our SPSS software. I've opened my own already. Then we have the data set. So I've imported my data set, but I can still do it again. So you go to file for the sake of those ones that weren't attending when we did other previous classes. So you go to file, you go to open. So we want to open new data. So remember to change your file extension. Then this is the one I want to use, the crude oil price. So open, yeah, okay. So I'm having this, yes. So let me close the other one. How come? No, I don't save. Okay, we can leave this one. So now this is the data set that we'll be using. Now you will find out that we have the year, which is our time series, the time itself, the month as well. But one thing is about this, there's a problem about this data set. Why? Because now if you want to analyze, do we analyze using the year or the month? But SPSS in a way has helped us because we can, it's not as if we are manipulating, but we can actually make it so that we can join the two together. So now to join the two together, this is what we do. You go to your data, then you define dates. Now this data set is measured in both month and year. So now I have years. So the different cases you can have, we have years and quarters, we have years and months. But this is the one that we want, years and months. Now remember that our data set is starting from 2015, from 2015. So that means I'll be changing it here. So I'll be having 2015. And remember, it is the month is what in one from month one, that's from January to December. So I'll click on OK. Okay. So the following new variables are being created. So this is what we have now. So now you can see. So we have January 2015, February 2015, March 2015. If not for thanks to SPSS for this function, because if not for this now, you will now have to manually typing the joint date by yourself. You now start typing January 2015 like that. But because of this functioning on SPSS, we're able to now you can see that we have from January to February, March 2015 up to December. Now after December 2015, the next thing we're having is January 2016, if and up to December. So all this, so this is where the data set stops for 2021. So that means what we are doing now, the purpose of this time series analysis is to analyze the crude oil price from the year 2015 to 2021, and to also forecast for the year 2020. Now we are going to see how much will they be selling crude oil price as year 2020. So that's what we'll be doing now. But before then, I want our data to look more beautiful. So I want to reduce the number of decimals that I have here. So you go to the data view, it has reduced. Now it's looking more okay. So now for me, I can add my label to, let's say I want it to be crude oil. Yes, crude oil price from year 2015 to 2021. So that's the label that I'll be giving them, I'm giving to that particular variable. So now what's the now if I want to run my analysis now, the time that I'll be using now will be this date itself and the crude oil. So I won't be using this one again. But let's just test run it. There's nothing, but let me just show you. Let's just see how it will look like when we use year or month and to analyze with our crude oil. So let's start now. So you go to your analyze. You go to analyze. The next thing you'll be having, the next thing where you go to for your time series or whatever thing that concerns time series, this is done under the forecasting menu. So you go to forecasting. Now I want to see how my time series looks like. So I'll click on the sequence chart. So now let's now use the year to just run our analysis. Let's use the year. So we send the year to the time axis label. Now you see what I was saying earlier on. If I were to be using the binary logistic data to run the time series, you see that there is no space for the binary logistic. Now which one from that binary logistic now? Except if there's a time column on that data set, I'm okay with that one. But if there is no time column, maybe like let's say days, week or month or year, you now want to run it as a time series analysis, you are so wrong. So you use the year, then want to use the crude oil as the variables. So let's now see. Click on OK. Let's see what it will give us. Let's see. It's loading. Let's hold on for it. Okay. So it's still processing. So why is this thing slow like this? Sorry, please, let's just hold on. Okay, it's up now. So now we can see how it looks like. This is 2015, 2015, 2015, 2015. Then I don't know, maybe we'll bend our phone to see it very well. Then the next one we have is 2016, 2016. For me, it is not informative enough. It is not informative enough. Yes, I have the year, but for me it is not informative. I need more details. What if someone that maybe I'm presenting to my shareholders or the shareholders of a company, how do I explain to them that okay, this one have 15, this one 15, this one, how many times don't you have 15 in a year? So this is not informative enough. So let's see that of months. Let's see when we use months. So you come back to your forecasting, you click on sequence chart. So let's send back my year back. Now let's use months as our time axis label. So the same thing. Oh, this is even the worst. Now you see 1, 3, 5, 7, 9, 11. Meaning, what does it mean? How do we interpret this? As an analyst, you should be able to visualize and make your visualization to your plots or whatever visualization tools you are using to be informative. So now let's now check the one that I was talking about. Let's use analyze and you come back to this. Then we have the sequence chart. Now let's now send back this month back. Then we have the dates format to be the time. So Okay, exactly. This is nice. So now we have it as at January 2015. This is what we have as at April 2015. At least this one is better than the two previous one that we had. So this is what we now have as our this is our visualization from the data um from the time series data that we had. So from this now, can you compare this to when we have a stationary data that looks like this? Yes. Now you can see that it is nothing close to this at all. It is nothing close to being stationary. So now you will notice that this at the point there is not even point zero here. There is no on the y-axis we don't have the zero points here. But you notice that at least the way this one they are far away from each other. You come here, it is far, it is going deep at this point, it is going up again here, it is coming down again. So now this data itself, it is not stationary. Why? Now we can now call in our ACF and PSF, that's autocorrelation. So the hypothesis there is that the H naught is it is not stationary. The second one is it is stationary. So now another way to check, we see from our plots here that the data is not stationary enough. When you click on autocorrelation now, it is loading. Autocorrelation. So the variable we want to apply is the crude oil. Now let's see. Let's see. Here we have it. Now at this point, please can we all hear me? Hello, can we all hear?
Yes, I can hear you.
Yes, ma.
Yes.
I can hear
Move
you.
on, ma.
Thank God. Okay. So let's
Bides,
do.
please, can you please mute yourself? Thank you.
So at this point now, you can see that the lag, this is the lag that I was talking about. You see that this lag number now it is at 16. So if I want to increase my lag, I can also increase it, but we'll do that later on. But I want us to establish an explanation from this ACF. Now, from this ACF, we can now see that the lag 1, lag 2, lag 3, lag 4, up to this lag 7. This lag 7, it is very sick. It is having a high correlation, especially as lag 1 and lag 2 compared to this ones here. Now this is the significance bond. This straight line here is the significance bond. Once your lag value is higher, or is has gone beyond the significance bond, that means there is a correlation between the data points itself compared to this one. From this point here, from this one, this is, I think it's 8, when we have 1, 2, 3, 4, 5, 6, 7, 8. So now from lag 8 down to this point 16, there is no autocorrelation. I don't know whether you understand. There is no autocorrelation. But yes, this one, they are negative autocorrelation, which is still okay. Still okay. But compared to the ones that we are having here that are high, that means the data itself, it is not stationary. So now, to not make data stationary, that's when we apply the difference of 1, or we apply the logarithm function itself. So let's come to the analyze again. Analyze, kilo shele. Analyze, yes. Forecasting. Then now, let's come back to the sequence chart. So from your sequence chart, you'll be able to get your chart. That's, instead of you doing the line chart of your time sheet, you can just come to sequence charts under the forecasting menu. So still at the same, we are still using the same variables here. Now let's apply our difference. Now you can change your difference to 5, whichever if you like. Whichever one you like. So we are using 1 for now. So we have okay. Oh, very good. Now this is the point 0. Now you can see that at least this is stationary enough. We can say it's stationary enough because the we can just say okay, it is only in May or maybe something around May, yes, close to May, that was farther away from the constant mean and variance. We can still accept this. But what if we now apply a logarithm function on the difference data set itself? Let's try it. So we come to forecasting, come back to that sequence chart again. Now we now apply a natural log to it. Okay, let's see. Okay, now you see that compare this with what we have here, now. You still notice that at that point again of May 2020, there is still a deepening again. It is still coming down. So you can, it is either we use the logarithm function or we use the difference function. But for me, I just prefer to use the difference function itself. So whichever one you want is acceptable. So now, after doing this, now we can now check. We've checked for our stationarity. Now we've made our data to be stationary by using a difference at point one, and we also examined using the logarithm function for the difference data itself. Now, having done this, now what's the next thing to do? Let's come back to our slide. Okay, so yeah, now. Sorry, please. My system is performing magic this night. Okay, it's back. Yeah. So now, okay, we've done the sequence chart to proceed with our time series. Now, the next step is from the above step, you can verify if the time series data is stationary. And if the data isn't stationary, then we perform the differencing transformation or the logarithm transformation, which we've done. Now, the next one is after after transforming the data and its stationarity, the next is to fit our ARIMA PDQ model, which will help us in obtaining a fitting model and also to forecast. Now let's stop at this point. Now let's come back again. Let's come back to our SPSS. So we have this now. Okay, this is the difference, this is the transfer. You can see we have transform difference one. So now let's now create, and I know I said earlier on that our ACF and PACF, that's the autocorrelation and the partial autocorrelation, we can use it to determine the values of our PDQ. Now you will notice that in our D, for our D, we difference only once. That means we've obtained the value of D, which is 1. Now we now have P and Q to now obtain. Now, when you go online, the truth is there is no specific way to obtain P and Q, but there is a direct way to obtain our D. That is why we make use of the information criteria where we have the PIC. So you can assume a lot of models, but when you analyze them, now it is not left to you to now know which of them, which among the models you've assumed, which among them has the lowest BIC. So the one that has the lowest BIC is the one that is your best candidate model. Do we get it? So now we can use the PACF to obtain our P, and we can also use the ACF to obtain our Q, which is the moving average. So now we come back to analyze, then we go back to the forecasting. Eh, forecasting. Sorry, please. Let's hold on. Why the system boots itself very well? Okay, let's come back again. Analyze. It's no longer moving. I don't know what's going on. Analyze. Oh. Please let's just hold on. Let's just hold on. Why it boots very well. Okay, I think it's back. Okay. Analyze, yes. Let's continue. Why now? Forecasting. Okay. So we go to the autocorrelation. So now let's remember that we transformed our data using the only one at point one difference. So we click on this to now, so it is to display what the autocorrelation and the partial autocorrelation. So we click on OK. Now let's see what it's going to give us. Okay, it's loading. It's loading. Okay, it's loading. Oh, very good. So we have we have our now we have our autocorrelation. Then another thing again I would like to mention is when you come to our programming or Python too, yes, for the programming languages, we have different tests, several tests to check for our autocorrelations. For R, we use LB test. We use what's the name? ADF, that's augmented dignifuller test, and several tests, but most of the time they make use of ADF. So for time series on SPSS, one of the statistic or the tests we make use of is the box logged Lejong statistic. So at this point, all the lag values are significant because they are less than our p-value, which is 0.05. So now this is our ACF plot. Now at this point now, our ACF, let's remember I said for the ACF, that's the moving average, we are obtaining the Q. But let's jump straight to the PACF. Now for the PACF, we use the PACF to obtain the autoregressive component, which is the model itself. Like, okay, if let's say we are having, if the value of our P is 3, that means we are having a 3 by Arima model. So at this point now, you see that it was only one at lag one that overpassed the boundaries. We can't be using 16 because before we get to 16, we had several lag values, so we can't use 16. So one thing I just want us to understand is when you are picking your values of P and Q, which when you check online, you won't see a definite answer. But most of the time, this is the application, this is the technique that is always used most of the time. So when you check out for your P and Q, it is always like maybe the first lag value to like the fifth lag value that you obtain the values, that's the value of your P and Q. So for our PACF, where we are obtaining the value of our P, we can see that the first lag is beyond and it has gone past our significance bound. So at this point, we can say the value of our P is 1. We can even assume that value of our P is also a 0. So now we have a 0 Arima model. That's one. The second one is we have 1 Arima model. That's value of our P. Now, a question you might be thinking, what if, let's say, take for example, don't get me wrong, please. Take for example, at this point, or no, let's do this ACF. Let's say this is how our PACF looks like. You know, the first one is beyond, the second one beyond, the third one, the fourth one, like that. So so at this point now, we can even make use of lag 1, lag 2, lag 3, lag 4, 5, 6, up to 7 as the model. So one thing about time series, you can have several models. There was one time I was to run an analysis for someone using R, and I was asked to use a function that's auto.arima function. And auto-arima function, it gives you, instead of you thinking of which model will I use or which one will I not use, you can use auto-arima function and it will give you several models. Several, you can have like 10, you can have 20 of them, several models. Now from the several models, besides several models that it will give you, take the best candidate model. The same thing for the AIC. When the value of the AIC is also low, you take that model to be the best candidate. So if auto does arima function gives a lot of models to use, the smallest one of the AIC is the one that will be the best candidate model. So instead of you thinking, that's why I said R is very robust. Like, it gives a lot of ideas for time series compared to SPSS. So now let's come back to the main one that we were doing before. So So now from the PSF now, so we've established that our model now is 0 and 1, is 0 and 1 model. That's value of our P. Now for the value of our D, at the two models that we've chosen, we will be using 1 and 1 because we differenced 1. Now what is now the value of our Q now? That's when we now use the ACF itself. Now at this point, yes, this is the ACF now. You will notice that at lag 1, at lag 1, this lag number 1, yes, so it sounds like lag 1. Sorry, so at lag number 1, we have this plot to be higher or pass, it's overpass the significance bound. Now we can say that number 3 pass the significance bound, but slightly, like slightly, it's slightly past the significance bound. But look at for the lag 2 plot, the lag 2 one did not overpass, so we can't just jump to 3 like that. We can't just jump to 3. So we can, it's still okay if we assume that our model or our what's the name, the value of our Q, yes, is also is 0 or is also 1. We can just use 1 1 for the both. We can just use 1 1. Remember I said there is no particular way to get all these values, so you can just assume different things. So it's not left to you to now perform the BIC model, BIC criteria, to now choose the best one among them. So now that means we're having two models. So we have 0 1 1, then we have 0 1 1 1 1, Arima model. So now having done this, we've chosen our Arima model. Now you now come to analyze. Now we now want to forecast using this model. Now by the time we now forecast, we will not be able to see the best candidates among these two models we've chosen. So we come to forecast, we come to the create model. Then the dependent variable is what? What's our variable of interest? We throw it here. Now, what type of method are we using? We have the ARIMA method. Now, what's the criteria that we are using? Remember that our data set is no longer stationary, is no longer non-stationary. If it were to be non-stationary, it is classified under stationary. But now that it is now stationary, that means we've removed the seasonality trend. That means our time series is not affected by seasonal trends again, and it is not affected by whatsoever trend, be it cyclical or irregular. So now, from our autoregressive, which is P, we have the first one to be 0. Oh, sorry. We have first one to be 0. The next one we have is, we have 1, which is our difference. Then we have the Q to be 1 as well. So this is what we have here. So you click on continue. Now we now come to statistics. What do I want SPSS to display for me? So at this point, I need the statistics of this parameter, my parameter estimates now, and I need the residual for ACF, the residual for PSF. We are still coming to this one as well. So at this point, I want it to display my forecast as well, like the predicted values I will be having. So yes, this is the most important, the normalized BIC, the BIC, the variation information criterion they were talking about. Then now, what plots do I need from here? So I need my observed values. That's the ones, that's my original data. Then I also want the forecast as well. I want it to forecast my predicted values. Then I also want a confidence interval for my forecast. Then I also want this and this as well. Then I also need my BIC plot too. So now we don't need anything here. And this is just the predicted values, then the lower limits and upper limits, which we are still coming back to when we get our results. So we come to options now. This is the forecast period. So the first option here, it says first case after end of estimation period, true last case inactive data set. So that means you still want to continue using your original data set. But what if for the second one, I want you to create to create new predicted values from that first case after the end of estimation period through a specified date. Now remember that in our original data set we stopped at December 2021, so, and we said we want to forecast for 2022. So that means I can come here, I will put 2022 for the year 2022. Then I come to the month. Till when do I want it? Do you want it to be 6 months? Do you want it to be 9 months? So we can just choose 6 months. That's from January to June. Yes. So now I click on, there's nothing else we need here. So we click on OK. So this will take a little while before it loads. So okay. Oh, she's done already. Yes. So now let's come to the time series modeler. Now look at the model type. So we use model 011. Then this is just the plus for the normalized BIC. We doesn't have much things to explain. But this is where we need from this model fit. This is the most important of them all, the normalized BIC. So at this point, we have 3.693 to be the number of normalized BIC, which we can also obtain at this point, at this place too, from the model statistics. So the ARIMA model parameters. Okay, so these are the estimates. These are the estimates for the model parameters, which this is the basics. So in for our subsequent projects to come from the data clan, expect more. So we'll go deeper and deep in all these things that you need to know. So for this, the ARIMA model parameters, so we have the residual ACF. So this one, instead of you checking for the values, we just majorly need the plots. It's the plots that we need. So for me now, we have the residual PACF. Yes. Then now for this residual, okay, these are our forecasts here. So for January 2022, the crude oil price will be 81.09. Now this year UCL means the upper confidence level and the lower. So one thing to note is, just like you having your confidence interval, it's same thing as having your confidence interval. That means even if our forecast value, that's 81.09, is not correct, the forecast, the true one, that's, let's say we are in that 2022, the true value itself would be between this 93 and this 69. That is why we have confidence interval. Do you understand? So at this point, my value shouldn't exceed, that's the real value, that's when it happens. So it shouldn't exceed 93.03 and 69.6. So this is the lowest value it can ever attain, and this is the highest value it can ever attain. So the same thing for, and remember we did it up to 6 months, so we had it up till the month of June. So this is just basically what the forecast is. Then we now have the residual. So for this residual, it's just like you having, let's remember that time series analysis is also a particular, is an aspect as well in what's the name, in regression analysis. So for regression analysis, you always have this error term. You always have this error term that gives more explanation our data set. So because when we check these lag values that we have, up from 1 to 24, you can see that none of them pass the significance bound. So at this point, we can say we don't have problem with the residual. That's just, but once it passes that over bound, it is a different case entirely. But most of the times, we don't actually do this residual part of it. We just most times, yes, we do it, and most times we don't actually do it too. So most at times, again, it doesn't pass that bound, but because you've already made your data to be stationary. So had it been your data is not stationary enough, there's high chances that your residual value, or the residual lag values, will be overpassing this significance bound. So now, good. So this is the forecast plus. Remember that this red part, that's the observed, is the main data that we have. And at this point, what after this line, anything that comes after this line is our forecast values. So you see that this one of them is the LCL, while the other one is the UCL. So with this now, this from this point, our forecast value will be from this point to this point now. So that's that for the model of 011. So what if we now want to create model of 111? So you come back again to analyze. So we don't have much things to change. We just go to the criteria straight. So let's create the model. So you still come back to, we are still doing the same thing, but we only come here to change this to be 1. So we have continue and we have okay. So now we will now compare which among them has the least BIC value. So now our model type is 111. So from here now, so what's our BIC? That's 3.758. So we can still come here. Okay, still the same thing, 3.758, still the same thing. Our lag value. Okay, now let's now check if our lag values, our forecast values are different. So we have 81.05 and this one. Let's register that. So let's come down to yeah. Let's come. Okay, we still have 81.09. That tells us that there is no change in our forecast value. Abi, is there a change? 1 point. Okay, there is a slight change. This one is 81.05 and this one is 93.06. And the one we're having here is okay, there is a slight change in our forecast value as well. So now let's now check for the residual now. Do we have is there anyone that is beyond? No. So we don't have problem with our residual. So that means our data points, our data set itself is stationary. Now the baba of them all, now we want to check if our models are correct now. So how do we now check for our models which is correct? So for the first one, we had our model to be what? Model, this is model 111, Arima 111, and we have 3.758 to be, abi, is that it? Yes, 3.758, yes, to be our BIC. Now, that's for the second one. Now, the first one is what? Arima 011. This is 3.693. So that means that Arima 011 is the best candidate. Why? Because it has the lowest number of BIC. So that's all about you forecasting or having or you creating your model. So I think when you come back to your this one here, okay, I want to show us how to get our forecast values, because by the time you are doing the analysis, you will need to obtain the values, the new predicted values. So by the time you come to your analyze, let me see if you can still get it. So you have the forecasting, then you come back, yes, you come back to the create model. So you go to that place where you yes, from that save. So I need the predicted values, I need the lower and I need the upper, and this one is unnecessary, so you can click on OK. So it will still repeat the from the output, it still repeats itself with the model that was there. But what I want us to check is this part of it. Yes, very good. Now this is the predicted crude oil model one, and this one for the lower and the upper. So now you now come down. Sorry, when you come down here for 2022, now you will now see the values itself. So you can now copy this one straight up to your report writing that okay, oh, this is the forecasted values that I have for my for my year, yes, for year 2020, from the month of January to June. That's for 6 months. So that's basically all about forecasting and the Arima model. So I want us to expect more from Data Clan. In our subsequent projects, we'll come straight with other things like a lot. Just expect more from us, yes. So I want to thank the Data Clan community for giving me the chance and the opportunity to share this knowledge that I have, this little knowledge that I have with just okay. Someone is raising and how do we do this one now? Can you unmute yourself then? Unmute yourself, Dari.
Okay. Thank you so much, Miss
Welcome.
Oluchi.
Yeah, welcome.
Honestly, I've learned a lot from what you taught us this night. So,
Okay.
I have questions, sir, and
Questions.
yeah, fortunately, you've answered like 3 of the questions during the presentation.
Thank God.
And okay, let me go straight to the point. Number one question is
Okay.
does does correlation affect time series? And
Yes.
okay,
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 go
okay,
on,
yeah.
go on. No, go on, go
Okay,
on.
does correlation affect time series? And the second question is, how can we deal with a correlation if there is a correlation in a data set, that time series data set? So how can we deal with it? How can we do it? In regression, there are ways to deal with correlations. So how can we do
Yeah.
that in time series? Thank you.
Okay. So, okay, that question is actually okay, and it's something that it is true. But what I want us to know is that yes, time series is under regression analysis, yes. But when we come to regression, you can refer to it as correlation. But when we come to time series, we refer to it as autocorrelation. So the major issue that a time series data set will be having is autocorrelation, not actually correlation. But it's just like autocorrelation, and in the sense of this time series is the same thing as that of this the context of correlation for normal regression analysis. So when you have your autocorrelation issue, the best thing to do is, if you're having the issue of autocorrelation, that means, okay, let me take us back to our output here. When we had issues of, yes, from here now, this from this place, you see that we have significant lag values that went higher than the significance bound. Do you understand? So now, definitely this data is having the issue of autocorrelation. And from our presentation, I don't know whether it was there, whether I wrote it there. I made it to be that I made it for us to understand that when we have autocorrelation, it gives us values of autocorrelation of any plot. Okay, it is not here, but maybe I'll update the plot of, okay, yes, okay. The ACF plot is a plot of the coefficient of correlation between a time series and lags of itself. So the way we have correlation for regression analysis, the same way we have autocorrelation for time series. So the best thing to do at that point is to difference your data or perform the transformations. So you will notice that after we perform the transformations at this point, you know that it was not the same thing with the ACF that we were having after transforming. You can see the difference now. Now it has reduced the number of correlation among, or the number of autocorrelation we have among the variables, that's among the time itself. So yes, your time
Okay.
series can have issues of correlation, which is autocorrelation in time series, not actually correlation. If you check online and do your research, you will notice that correlation, the definition of correlation, which is when the variables have and when they are correlated, it is the same definition that you will see under that of autocorrelation. That's when the time series itself are autocorrelated with themselves. That's it. So definitely your time series can also have this issue, and the best solution to do is to transform the data. And you can keep on differencing to be able to, or you increase your lag values for R increases values to be able to get a more stationary data. But for SPSS, yeah, the best thing to do is to perform your logarithm transformation and the difference as well. So I believe I have answered your question now.
Yes, thank you so much.
Okay.
And I want to ask another question, ma.
Ewo. Okay.
Okay, please, I don't know if because at some point I was lost during the presentation,
Okay.
so I don't know if you've mentioned it before. Okay, one of the question. Okay, the question is there a way we can test for the significance of the model we are using on time series?
Yes,
Thank
yes, you can test for it. Like I said earlier on, I said this before. You can, for R gives more robust more chances for time series where you can use the ADF, the LB test. But for SPSS, the one we are limited to is the box link jung. So but for that box link jung statistic, let me look for the output itself. Okay, yeah, I think this is it here. So at this point, most times, from based on my experience, I'm not actually saying it is wrong or whatever, but based on my experience, I've come to understand that the model parameters you'll be using should be significant, yes, and it should be less than your p-value, which is 0.05. But at the same time, when you check the ARIMA model parameters at this significance point, you see that the lag 1 is less than it. So which makes that model to be significant enough because it is less than our p-value. Do you understand? Can
Yes,
I
ma.
get
Yes,
the
ma.
response? Yes. So for the L junk, most at times, based on my experience, like I said, most at times we don't actually use that L junk test very well. The best way to perform such significance is to use the programming languages. I'm not saying that SPSS is not okay for your time series. You can see what we did on time series. Well, it's just straightforward. That's if you know where you go to. But to get more definite and specific answers, use the programming languages to do your time series and you will get more answers. And at this point in time, you can see that the significance value is less than the 0.05, which makes the model to be significant. Is that
Okay.
clear?
Yes, it's clear, ma. Thank you, ma.
You're welcome.
Yes, ma.
So, is there any other question?